Hello. In this video, I would like to revisit the procedure that we went through in class on Tuesday, how to program your TI Inspire to compute results from the quadratic formula. This will be particularly important for the assessment that you've been given and that I would like to have submitted by the end of the day, Friday of this week. You should have a fair amount of time in class on Thursday to complete this. And so if you program your calculator right away, I'm certain you can get through all 18 questions before you leave, and you can leave the assessment behind in class. Well, the first thing that we have to do is turn on the calculator and press the home button. In doing so, it brings you to this screen. And from this screen, we're going to choose option number 1 to create a new document. Now, if you're prompted to save the last user's work, we're going to say no to that. And instead, I just want to start a new calculator from scratch. So we'll choose option number 1. So we've now completed step 1 and step 2 and step 3. We've added the calculator. The next thing we need to do is we need to define the quadratic formula. And we're going to define QFP for the form of the quadratic formula that includes a plus symbol, and we'll use QFM for the form that uses a minus symbol. So it's only tedious this first time if you recall. So let's go ahead and type in here define. We'll need a space bar, and then QFP. QFP for quadratic formula plus. And the quadratic formula does require an A, a B, and a C input. We'll then choose the equal sign because the results of the quadratic formula plus will be dependent upon the results from this computation. When I press Control Divide, that'll create an empty fraction, and then we can build the equation. Negative B plus the square root, so Control and then this button will create the square root. Now we can write b squared minus 4 times a times c. I'm not sure if you can get away with skipping those multiplication buttons, but I always type them just to be safe. I would recommend that you do the same. When we jump down to the bottom of the denominator, we can type 2 times a, and now we're done. We've defined the quadratic formula plus to be dependent upon a, b, and c, and then this is the formula to be executed. And we'll just press enter. Now the program has been stored. If we press the up arrow twice, then this expression is highlighted, and we can tap the enter key to copy it down. We're copying it down because we need to create a second equation, this time with a minus sign instead of a plus sign. We're going to rename this formula as the quadratic formula minus, so QFM. And now we have the calculator set up and ready to solve any problem that we encounter on our assessment. And that takes us through step 4 and 5. As a reminder, when your quadratic equation is written in this form, ax squared plus bx plus c equals 0, you can enter the coefficients a, b, and c into the functions above, the QFP and QFM. The calculator will compute real number results. This is the example that we had in class. I'm going to choose another example to complete down below. But essentially, we have to make sure that all terms are moved to the left-hand side, correctly identify our a, b, and c values, and then we will run both the quadratic formula plus and the quadratic formula minus. So we've done this one in class. This one looks like fun. Let's do number 13 here. With number 13, again, we need to move all terms to the left-hand side. So I'm going to do this all in one shot. I'll subtract 8 from both sides of the equation. I'll have to subtract 4r from both sides of the equation, and I'll have to add 3r squared to both sides of the equation. Doing so will effectively cancel all of these terms on the right side, and we'll be left with 0, which is what we're after. And on the left-hand side, well, we'll combine like terms. So 2r squared can be combined with 3r squared. That makes 5r squared. The 5r and the 4r, negative 4r, can be combined to make 1r. You can write it as 1r or just r by itself. And then lastly, since we subtracted 8 and there were no like terms to combine it with, then it's going to stay as a negative 8 as it is. We do need to correctly identify our a, b, and c values in order to obtain correct results from the quadratic formula. And remember, the a, b, and c values come from the coefficients in front of the letters, and then this last number that's all by itself. So really I should have the number 1 highlighted here, not the letter r. So our a value is 5, our b value is 1. Whether you wrote it or not, there's an implied 1 that multiplies by this r. And our c value has to be negative 8. Keep in mind that the symbol, plus or minus, in front of the number is part of that number itself. So here's what I would like to see as your results for the use of the quadratic formula. I would like for you to write QFP for quadratic formula plus and QFM for quadratic formula minus for every one of your results on this test. In fact, I would also like to see your work in which that you had to do in order to isolate the terms as well. So everything that you see here for number 13 I think would be important to show. At this point we can go to the calculator again and execute the QFP and QFM. So the quadratic formula plus evaluated at the values 1, and negative 8. Those were our a, b, and c values. Well, that ends up being this result. Now, depending on which calculator you use, in the classroom you'll probably get a decimal result here instead of a precise answer. And that's because the calculator that's installed on your computer is this CAS model, an algebra model. So I'll accept either answer, either this one, or if the calculator returns a decimal, that would be fine too. Personally, I like 4 decimal places for accuracy, and if we round to the 4th decimal place, this 8 turns to a 9. So for my QFP result, I'm going to say 1.18, correction, 1689, and then I'll do the same thing for the QF minus. So QF minus. We'll use the same numbers because we're evaluating the same formula in 2 different directions, which is necessary to obtain our 2 results. And when I calculate the quadratic formula minus, I get negative 1.3689. Negative 1.3689. And these are the 2 solutions to this particular example. I said it before and I'll say it again. We recognize that there should be 2 solutions to this particular problem, and if we were to guess and check to find the 2 numbers that make this particular expression equal to 0, or to make this left side of the equation equal to the right side of the equation, we would be here a long time guessing and checking. In fact, these decimals were much longer than what we see here, and that would make guessing and checking even that much more difficult. So certainly the use of a calculator is very, very nice. Additionally, this type of calculator provides us with more precision than a graph normally does. Another way that we could solve this problem, albeit with slightly less accuracy, is to graph the left side of the equation once we have it equal to 0. Now, I'm going to change these letter r's back to x because some graphing calculators don't like any letter other than x. So I'm going to use x here, and I'm going to say that 5x squared plus x minus 8 is the graph that I'm after. But if I tap on the screen, I see the same results, 1.169 and negative 1.369. Those are the same results that I got here, but with less accuracy. And if I were to try to identify those positions without the aid of a calculator tell me those precise locations, it would be very hard for me to specify that location because this graph just doesn't seem to align very well with a precise lattice point or a precise point or portion of the graph itself. So while graphs are nice, they're not always perfect. They're not going to give us the best solution in all cases. Now I'm going to use this example to complete one of the graphs on the back side of our handout, because there are 4 graphs that I'd like for you to complete as part of this assessment as well. We've already identified the 2 solutions to this problem on the x-axis. Those were given to us by the quadratic formula. So what I would like for you to do is to recreate the graph either from Desmos or by using your clues from the quadratic formula. And we're going to do so on this graph back here. So the equation number that I'm referencing is number 13. This is coming from number 13. And the 2 x-intercepts are the quadratic formula results that we just established. So we've got 1.1689 and negative 1.3689. Now the y-intercept, that's actually pretty easy to identify, whether you have a graphing calculator or not. The y-intercept is always the same as the c-value once you have the expression equal to 0. And we can see that down here. The point at which the graph touched the y-axis or crossed the y-axis is at negative 8. So we will report that. And the vertex, well, that's a little bit harder to find. There are shortcuts in which we can use the calculator, but if you've got access to Desmos, I think this is the fastest way. The vertex is the lowest point of an upward-facing parabola, or it would be the highest point of a downward-facing parabola. This point, this key data point, often shows up as a light gray dot on this quadratic graph until you click on it with Desmos. And now we have the coordinate negative 0.1, negative 8.05. So we'll actually locate the vertex as a coordinate, negative 0.1, comma, negative 8.05. With those key data points, we can now recreate the graph. We've got an xy axis, and depending on how you want to scale this, it's fine if you want to change it. I think I'm going to go every 2 grid lines on the x-axis that represent 1 unit. So now 1.16, well, that's a little bit bigger than 1, but less than 1.5. So I'm going to say that that data point exists right about here. And negative 1.36, same thing. It's a little bit less than 1, but not quite negative 1.5. So I'll put a dot right here. We've got a y-intercept at negative 8. 1, 2, 3, 4, 5, 6, 7, 8. And then the peak of this graph, or the valley in this case, the vertex, was negative 1/10, so just a little bit less left of the origin and down negative 8.505. So that's just a little bit lower here. It's a little bit tight with these 2 data points, but at least we've got 3 well visible coordinates that we can actually connect with a nice curved line and try to recreate this U-shaped graph. Part of being a good math student is being able to interpret the behavior of a function, and the way we often do that is by recreating sketches of graphs with or without the use of a calculator. Now there are only 4 graphs that I'd like for you to recreate, and it can be any one of the, or any 4 of the 18 problems that you were faced with. I'm willing to bet that the first 4, for example, are going to be a lot easier to graph than anything down below. So I'll leave that up to you which graphs you want to recreate, but I do expect to see solutions for all problems 1 through 18 using the quadratic formula and reporting your results this way. Isolate the equation, identify A, B, and C, and use the quadratic formula to determine your 2 results. If you have further questions, please let me know. Otherwise, thanks for watching.